So like I said, today we're going over sequences. Next class is series. Now you have touched on sequences before. You've done it a little bit in Algebra 1. I know this because I taught summer school Algebra 1 and they did it. So you guys definitely did it. Then we did it in geometry. And I know it's been 3 years since you've done geometry, but here we are. This isn't the first time you've seen these. And they're pretty intuitive. It's just a sequence is a list of numbers. It can either be finite or it can be infinite, meaning it goes on forever. And it is a listing of numbers, and the numbers inside of a sequence are called terms. And each term is in a certain position in the sequence. So if a term is in the first sequence, we say that this term is term A1. If a term is in the second position, we call this term A2 and A3 and so on until we get to A sub n, which n can be any position in the sequence. N is any number. And the whole entire sequence can be called A sub n. What else? I think that's it for the intro. That's basically all that this is saying here. You can have a finite, which means it ends, or an infinite sequence, which ... means it goes on forever. Yeah. Oh, and each term, like I said, is denoted with a lowercase letter with subscripts. So A sub 1 is term number 1. A sub 2 is term number 2. A sub 3 is term number 3. All right. Now, there are two different ways to define a sequence: explicitly and recursively. First, we're going to go over explicitly. Explicitly defined sequences allow you to find any term in a sequence. Any term. Versus recursively allows you to build from one term to another. So recursively, in order to know a certain term, you need to know another term in the sequence. How do you type a subscript in the calculator? You don't. It's kind of like the label that goes on it, Karina. So like, if we had this sequence, this is in position A1, A2, A3. It's how we label each one of the positions. You don't have to type it into the calculator. Okay. So, let's work with explicitly defined sequences first. We're trying to find the first 4 terms of A sub k is equal to 3k plus 4. So if we're trying to find the first position, the first term, this would be term A1. And what we're doing is we're taking that k value of 1 and we just plug it in for k. 3 times 1 is 3 plus 4 is 7. So the first term in our sequence is 7. Oh, I forgot to mention. Sequences are written in set notation. So just like we do domain and range sometimes in set notation with the squiggly bracket, we do sequences in set notation. Okay. Then we do the same thing to find the second term, A sub 2. But this time we're plugging in 2 instead of 1. 3 times 2 is 6 plus 4 is 10. So our second term is 10. Whoa. I need to unplug that, I guess. A sub 3. Plug in 3 this time. 9 plus 4 is 13. So our third term is 13. And A sub 4, whoops, is 3 times 4 plus 4. 12 plus 4 is 16. So those are the first 4 terms of the sequence. Pretty straightforward. We're just plugging in the term number to find the term values. You can find any term in the sequence. You could find the millionth term if you wanted. All you have to do is plug in the term number into your explicitly defined sequence. So this would be 304. I guess we could quickly do number 2. It works the same way. Do we have to write out how we found each term? No. No, you do not for sure. You can just do it in your head. So if I'm trying to find the first term, that means k is 1. 1 raised to the power of negative 2. Remember, over here, anything raised to a negative number can be rewritten in a denominator with the positive version of that exponent. So 1 over 1 squared is just 1. 2 times 1 is 2. Then we plug in 2. 2 raised to the power of negative 2 is actually 1/4. So 2 times 1/4 is 1/2. 3 raised to the power of negative 2 is actually 1/9. 2 times 1/9 is 2/9. 4 raised to the power of negative 2 is actually 1/16. 2 over 1/16, 2 over 16 is equal to 1/8. Those are the first 4 terms. And the 100th term, we do just like we did in the previous problem. Actually 2 over 10,000, which is equivalent to 1 over 5,000. Any questions so far on looking at explicitly defined sequences? So now recursively defined, which I like explicitly defined. Like I want things to just be straightforward. I don't want to have to know something else in order to find something in the future, right? Probably because I'm lazy. But a recursively defined sequence is just like I said, you need to know a prior term to know a future term. Now, normally, the term being defined is always your first term. So here, looking at both of these examples, they tell you what B sub 1 is. They tell you what A sub 1 is. Then, they define the sequence B sub n, by Conrad, is equal to 0.5 times B sub n minus 1. Now what this means, n minus 1, this is the previous term in the sequence. So if you were trying to find the 5th term of the sequence, you would need to look at 5 minus 1 is 4, the 4th term in the sequence, the term right before it. So it wants us to find the first 5 terms. If I'm trying to find B sub 2, we already know the first term is 32. Great. If I'm trying to find B sub 2, I take 0.5 and I multiply it by B. Now our n in this position, our n in this term is 2, minus 1, is B sub 1. So I'm looking at B sub 1, which I know is 32, and 0.5 times 32 is 16. This is a very complex and convoluted way to say we're just multiplying by a half every time. So 32 times a half is 16. Okay. 16 times a half is 8. Okay. 8 times a half is 4. 4 times a half is 2. Done. I mean, it's really easy to say it verbally, right? But you would always wonder, okay, how would you write that mathematically? How would you write an equation so that you could know any term in the sequence? Well, this is the recursive way we would write it. Okay. Let's see. Do we need to do all of these? I'm going to say let's skip 4 and just look at 5. So this one's a little different in that the first and second term are the same. Okay, no big deal. It's all right. Then, it states that the rest of the sequence is defined by b sub n is equal to b sub n minus 1, which remember, we know this is the previous term, plus b sub n minus 2. This means 2 terms ago. Probably not the best vocabulary usage there, but that's how I think about it in my head. It's 2 terms in the past. So if I'm looking at my third term, b sub 3, I know that I'm going to have to take the term right before it, which is b sub 2. That's this one. And I need to add b sub 1, 2 terms from our position b3. So I'm adding 1 plus 1 and I get 2. What do you think b sub 4 is going to be equal to? Yes, 2 plus 1, right? We're adding the pre-term, which is b3, and the 2 terms ago, which is b2. So 2 plus 1 is 3. What about b sub 5? Good. And lastly, b sub 6. 8, yes. Now does this seem familiar to anybody? This is a long stretch, but someone last class actually knew it. Seems tedious. Yes, guys, yes. How do you guys know that? I'm just curious. I can't either. Crap. Fib. I read it in a book. Science videos. I think it's that. Might be too many double letters. Fibonacci sequence. Do you need to know this for this class? No, not at all. It's just a very famous sequence. Kind of catchy. 1B. Oh, thank you. I am an awful speller. All right. I almost want to come back to this limit stuff because it makes no sense where it is in the lesson. Somebody's got to remind me though. Where do I want to put it? Where do I want to put it? I can put it right here. Go back. Do limits. All right. I'm going to skip limits for now. It doesn't make sense in the flow of things. We'll go back to it. All right, so we just learned about the 2 ways to write or define sequences. Now we're going to learn about 2 different types of sequences. Now these are not the only types of sequences. These are the major and easiest sequences that we could have here. Arithmetic and geometric. These are the 2 types of sequences that you went over in Algebra 1. And also the 2 types you went over in geometry. A sequence can for sure be neither of these things. And in fact, most sequences are neither of these things. These just happen to be the 2 most famous and therefore easiest. Easiest and therefore most famous? Not quite sure. Okay. Bottom line, Arithmetic is when you add or subtract to get to next term. Geometric is when you multiply or divide. But I say multiply or divide, but it's always going to be multiply. Like if you say, oh, you're dividing by 2, you're actually multiplying by a half, if that makes sense, okay? Multiply to get to next term. Now, when we have an arithmetic sequence, we're adding and subtracting to get to the next term. The difference between two successive terms is always constant in this case. And that difference is called the common difference, and it's denoted as D. It's denoted as D. And just like I was explaining before, there's two ways to define this arithmetic sequence. One is explicitly, and the second is recursively. Remembering that, and I don't know why they didn't put it here, but when we do recursive, when we are recursively defining, we need to state what the first term's number is. A sub 1. We need to put what number that first term has. Geometric is when we multiply to get to the next term. Now, in order to know how to find that multiplication or that ratio, that common ratio it's called, R, we just take the second term, forgot the R, and divide it by the first term. Right, basically you're just finding how much you multiplied by. That's all you're doing here. So the next couple of examples, we have to, when we're recursively writing a geometric sequence, we have to also state the first term's value. Okay, so the next couple of examples want you to identify, are these sequences arithmetic, geometric, and state their rules, their definitions, and find a certain term in the sequence. Now, I don't like this because I wish that they would introduce some that are neither here. Because we will not always have either arithmetic or geometric. Sometimes they will be neither of these things, but just keep that in mind as we're doing these. Okay, so Part A, find the explicit rule and the 20th term for this sequence. What do you guys think? Is this arithmetic or geometric? You know, there are no students in here. I've had my mask on this entire time, and Conrad left forever ago. Yes, it is arithmetic. Why? Yes, we add 7 every time. We add 7. And it wants us to explicitly write the rule. So I'm looking up here at arithmetic. And it states, if I'm trying to explicitly write an arithmetic sequence, we write A sub n is equal to, let me do a different color. I don't know why orange is not usually my favorite. A sub n is equal to A sub 1. What is A sub 1? Five, good. So you literally write down 5. Plus D, what's our D? Seven times n minus 1. And we're done. Well, we're done writing the definition. the rule, the equation. But then it asks us to find the 20th term, which all we have to do, just like we did in the beginning, is plug in 20 for n. So 20 minus 1 is 19. 7 times 19 is 133. Plus 5 is 138. And that's it. Part B has 9, 12, 16, 21, and a third. What do you think for this one? At first, you would think, oh, you're increasing by 3. But then going from 12 to 16, you're increasing by 4. Recursive is a way to write it out. It's not the type. We're looking, is this arithmetic or geometric? Are we adding, subtracting, or are we multiplying? We are actually multiplying. Now, sometimes it's not going to be so easy to see what you're multiplying by. What you do is you take the second term and you divide it by the first term. So you have 4/3. And then if we were in any other situation, you would want to check. 9 times 12 is 4/3. I'm sorry, 9 times 12. 9 times 4/3 is 12. Is 12 times 4/3 16? Yes, it is. Is 16 times 4/3 21 and 1/3? Yes, it is. If your answer is ever no, then you've come up, it is not a geometric and you've come up with the wrong rule. Okay, so it is geometric. And we're going to explicitly write the rule again, but this time for geometric. So we have a sub n is equal to a sub 1, which is 9, times the ratio, or the rate, 4/3, raised to n minus 1. Then it wants us to find the 8th term, so we just plug in 8 for n. Whoa. And then we just really quickly do 9 times 4/3 raised to 8 minus 1 is 7. 67. 4, 2, 4. Now we're not going to fully do out the next couple because I think it's repetitive, but I do think we need practice with identifying arithmetic or geometric. So, part C. Is this one arithmetic or geometric? Yes, it is arithmetic. Why? Plus 5, yeah. We're adding 5 every time. I wish they would have done one where you're subtracting because that's still arithmetic, but it's okay. What about D? What do you think for D? It is geometric. Why? Right. You multiply by 0.9 every time. Now, to find this number, you just take your second term divided by your first, which in this case is super easy. 0.9. And again, if we were in any other situation, you would want to check, is this true? Do I just multiply 0.9 times 0.9 to get 0.81? I do. Do I multiply 0.9 times 0.81 to get 0.729? I do. Okay, and then it says, for examples A and B above, write their recursive rule for each. So, for part A, we originally wrote it explicitly. Now we're writing it recursively. When we write recursively, we must state what the first term is. This is part of the definition we have to write for recursive. A sub 1 is 5. Then, it's what is that? Arithmetic. So we look up here at this rule. We need to write A sub n is equal to A sub n minus 1 plus D. And what was our D? It was 7. Our common difference was 7. And we're done. Part B, same thing. I need to write what is our first term. It is 9. This is a geometric, so I followed the geometric recursive definition of A sub n is equal to A sub n minus 1 times R. And our rate was 4/3. Normally, for following most rules, most ways that we write equations, we would write the constant in front of the variable. Either way. Are there any questions? Okay. I'm going to say we're not going to do this. We've already done this. It just wants us to find the first 5 terms of the sequence. Well, that's exactly like what we did on the very first page of these notes. So I don't think there's any point in doing it again. But this next example is important, I think. Because I think as a whole, I don't know about everybody. Maybe I'm just assuming everybody is me. But I, for one, struggle in seeing the sequence most times. It's hard to identify these sequences, and most people do struggle. Some people get it naturally, but others not so much. So the more practice we can get in identifying, the better. Identify the pattern and write the next 3 terms of the sequence. So part A has 2, 5, 10, and 17. First of all, is this arithmetic or geometric or neither, do you think? It is neither. Yes, it is neither. So we have to think a little bit outside the box. You have to think, what's happening with these numbers? Well, we can look at how much they're increasing by if we're multiplying each time. Yeah, I wouldn't think multiplying because 2 times 5 is not going to be the same as 5 times 10 and so on. But I do notice that going from 2 to 5 is plus 3. Going from 5 to 10 is plus 5, and going from 10 to 17 is plus 7. What does this tell us? What is interesting about these numbers? Not exponential. Close. What do you notice about these numbers? What do you see here? Our increase is increasing by 2 every time. Does anyone know what this line of differences is called? This is technically what is called our first difference. And if the first difference is the same, you know it's linear. You know it's arithmetic. If the second difference is the same, this is called the second difference. What do you know? What is this? Oh, does no one know? Should I just tell you? It's a quadratic. Ah. It's familiar, but I don't know what it is. It just means that we're going to have squared terms here. Yeah. So, okay, great. But if I just say a sub n is equal to a squared, and I plug in 1, does that give me my first term? What do you think I have to do? Oh, not a squared. Jeez, Miss Sunderland. N squared. What do you think I have to do to make it so that this is correct? Ah, yes, we just add 1 each time. Yes. So then it just wants us to find the next couple of terms. 4 squared is 6. Oh, that we already did 4. 5 squared is 25 plus 1 is 26. 6 squared is 36 plus 1 is 37. 7 squared is 49 plus 1 is 50. The next one is easier, I think. Whoops. We're trying to first define this, then find the next 3 terms. Ooh, that's way too many squiggles. Now, when we're dealing with fractions, sometimes it's easiest to think of these as separate terms, the numerator as a separate term from the denominator. And it's actually easier to address the denominator first here. So if I'm just looking at the denominators, what do you notice? Okay, we're increasing by 1 each, yes. But let's think in comparison to n being the term number. What is the similarity between the denominator and the term number, the position we are in? So let's see. This is a sub 1, this is a sub 2, a sub 3, a sub 4. What do you notice? Ah, they're the same. Our denominator is n. Our denominator is n. What do you notice about the numerator versus the term number, the n? What do you notice? Ah, n plus 1. Yes, we're taking the term number and we're just adding 1 every time. That's all. So our next would be 6/5. Then we would have 7/6 and 8/7. There are a few set rules for how to define sequences, but there's always going to be a brand new way that you didn't think of. You just kind of have to manipulate the numbers and think about how they relate back to n. Okay, so now I wanted to go back, way back, and do limits. Because now we've gone over, by the way, we've gone over how to define sequences. We've gone over some types of sequences. Now we're kind of just going over some extra information. We're going to be going over limits or end behavior of sequences. We're going to be going over what is called an arithmetic mean. We're kind of not really going to be going over graphing. And then we're just going to be going over a couple of examples, different questions they could ask you about sequences. So let's go back up to limits. Finding limits of an infinite sequence. Remember that limits is just a fancy way to say end behavior. What's happening at the end. end behavior. Whoops. Now, in order to find end behavior or a limit of a sequence, it is easiest to remember back to rationals. And remember how we identified horizontal asymptotes. We use that acronym Bobo, Bots, Eats DC. This also helps us to identify the limit of a sequence. So if I was to graphically show you what I mean by a limit, let's do this, right? Now I'm drawing that line to show you that this graph, as x approaches infinity, your y value approaches, well, we're going to say that that's 1. This is the end behavior, what's happening as x gets infinitely large. So the same thing for these sequences. As we get further and further in the terms, sometimes our sequence is going to be approaching a constant number. When the end behavior, when the limit does approach a constant number, we say that the sequence is converging. When your limit is equal to a real number. When you don't have a limit, or say you're approaching a non-real number, or your end behavior is oscillating, it's not approaching a single number, we say that your sequence is diverging. So, let's try it. Let's try to figure out what is happening to these sequences. Are they converging or diverging? And again, in order to know this, we need to know what the limit for the sequence is. And in order to know the limit, we need to think about this acronym, Bobo, Bots, Eats, DC. Now, unfortunately, to know the limit, we are going to have to know the definition for these sequences. So we are going to have to write down the equation, the definition, the rule for each one of these. What do you think the rule is for this part A? It's not arithmetic or geometric, so we have to think outside the box. Yes, Jack, exactly. Our numerator is, no matter what, always 1. Whereas our denominator is always equal to the term number, the n value. Right? This is a sub 1. This is a sub 2. These denominators are always the same as the n value. Someone's calling me and it's Austin, Texas. It's okay. I'll just answer later. All right. Now here comes the tricky part. I didn't think that this was the tricky part, but no one from, or it seemed like, no one from 7th period remembered at all how to find horizontal asymptotes in rationals. So look, before I explain anything, is this bigger on bottom? Bigger on top, or are the exponents the same? Yes. Thank you, Jack. Somebody. So look, we don't even have a variable in the numerator. What this basically means, or what this could mean, is we actually have an n sub 0 in the numerator. N sub 0 is equal to 1. So you ask yourself, is our invisible exponent of 1 bigger than 0. Yeah, it is. So this is bigger on bottom, which means our horizontal asymptote is at 0. This also means that the limit as n approaches infinity, so as the term number gets bigger and bigger and bigger, our term value gets closer and closer and closer to 0. It will never actually equal 0, but it will get closer and closer and closer to 0. So, is this a real number? Is 0 a real number? Hold on. Okay, so yes, 0 is a real number, so this is said to converge. It approaches a real number, so it is a converging, it is a converging sequence. Okay, so part B, same thing. First, we have to identify the rule. A sub n is equal to, now we can just think of the numerator separate from the denominator. How would you define this? Right. We've actually already looked at this, very similar sequence to this. It is n plus 1 over n. Now, do we have bigger on top, bigger on bottom, or are the exponents the same? Same. So we need to divide the coefficients. We have invisible ones as our coefficients. So 1 divided by 1 is 1. So, is this approaching a real number? Is it converging or diverging? Anybody? Yes, it is converging. Good. Oh, converging. Because it's going towards a real number. These ones are easier because they've already, well, some of them are easier. They already have the rules stated. They've already defined the sequence. So we just need to ask ourselves immediately, what's the limit? And we find the limit by doing the acronym Bobo-Botsi-CC. So, do we have bigger on top, bigger on bottom, or are the exponents the same? Bigger on bottom. Bigger on bottom means our limit is 0. So again, this is an example of converging. What about this? What about D? What do you notice about these numbers? This sequence. It's alternating or oscillating. Just like sine and cosine graphs oscillate. Because it's oscillating, it's not approaching a single number. What do you think this is? It diverges, yeah. because it's not approaching a single number. It's just going back and forth between between 1 and -1, like so. It's never approaching a single number. It does not have a limit. Okay. What about part F? Bigger on top, bigger on bottom, or the exponents the same? Bigger on top, S. What does that S stand for? Not same. No one remembers. Slant asymptote. There being a slant asymptote means it's not as you get to the end, as you go towards infinity for your value, you're not approaching a single number. It goes to all of these different numbers because it's a slant asymptote. So this is also diverges. All right, guys, that is time. I am going to record myself doing probably a couple of these and at least part B. Part B is the hardest part. I will record myself going over that. All right. So part B says, find the explicit rule of the geometric sequence if A sub 2 is equal to 3 and A sub is equal to 192. So they really don't give us much information here. My go-to first step, I like to visualize things. I like to put these in their respective positions in a sequence. So I'm going to go ahead and put blanks for the terms I don't know and insert the terms I do. So I know A sub 2 is 3, then I don't know 3, I don't know 4, I don't know 5, I don't know 6, I don't know 7, and I know 8 is 192. So this is A sub 2, and this is A sub 3. Now it does for us to tell us that this is a geometric sequence. So what we have to do first, we're going to have to solve for multiple variables, because when we're writing a geometric sequence, remember it's A sub 1 times r raised to n minus 1. So right now, we don't know what r is, and we don't know what A sub 1 is. We need to solve for both of those terms. So what I'm going to do first is I'm going to solve for A sub 1, the first term, in terms of r. So let's go ahead. I know that I'm trying to solve for A sub 1 in terms of r, and I know what A sub 2 is. So what I'm going to do is I'm going to set up the equation for A sub 2. And my n value for A sub 2 is 2. And the actual value of A sub 2 is 3. I'm just going to substitute A sub 2 for 3. And what I'm doing now is I'm just trying to, 2 minus 1 is 1. I am now trying to solve for A sub 1 in terms of r. Meaning I'm trying to get A sub 1, my first term all by itself, and I need to do that by dividing by r. So A sub 1 is actually equivalent to 3 over 8. So that's the first step 1. Second step is to use the other term they give us, A sub 8. So this was for A sub now we're doing the exact same thing, but for a sub 8. And we're again solving for a sub 1 in terms of r. And we're doing this because if we know what a sub 1 is equal to in both these equations, well, a sub 1 should be the same number. We can set them equal and then solve for r. So that's what we're doing. That's our grand goal. But first, let's go ahead and set up a sub 8. So a sub 8 is equal to a sub 1 times my rate raised to the power of 8 minus 1, which is 7. So a sub 8 is actually equal to 192, is equal to a sub 1 times r raised to the power of 7. This means that a sub 1 is actually equal to 192 divided by r to the power of 7. So now, both of the equations gave me a value for a sub 1. All you have to do is set these two values equal and solve for r. So anytime I have a fraction set equal to a fraction, how can I solve it? Yes, you can cross multiply. So we cross multiply here and we get 3r to the power of 7 is equal to 192r. Then if I divide both sides by r, I have 3r to the power of 6 is equal to 192. Divide 3 over, and I get r to the power of 6 is equal to 64. Then if I 6 root 64, r is equal to. So now I know what my r is. In order to find my, I'll do it up here. In order to find my first term, remember that the rate is equal to the second term over the first term. So if I know my rate is 2 and I know my second term is 3, this means that my first term is equal to 3 over 2. So now I can set up my entire equation. A sub n is equal to my first term, which is 3 over 2, times my rate, which is 2, times, or raised to the power of n minus 1, and I'm done. This is definitely the hardest one. Has lots of steps.